All right, let's take a look at section 15.10, which will be change of variables for double integrals. So learning objectives this time. We're going to use the change of variables to simplify a double integral and then define and calculate the Jacobian. So we can think of this kind of like a complex U substitution for two variables. The way that we're going to start by looking at that is by using transformations. An example is here in figure 1, where we're going to transform between two regions. So transform region S into region R. And if we have a particularly nice transformation, we can also use the inverse transformation to go back from region R to region S. And the sort of interesting points about these two regions is that R is the space where our traditional X and Y variables exist, but our region S is where we'll have our new variables U and V. So they'll be in this new region S. Usually S is a simple region, while R might be some complicated region. We'll choose our substitution variables U and V so that our simplified region S looks quite nice. But if we go with a more rigorous definition, transformation is a function that maps our variables U and V into the variables that we might have wanted to start with, like X and Y, where we'll consider X and Y to be functions of U and V. Here, they're listed as G and H instead of X and Y. So in other words, a transformation function is a function whose domain and range are both subsets in R2. So we happen to be working in R2. We're going to define a new term called C1, highlighted, highlighted right here. And we'll say that a transformation is C1 if all of the first order partial derivatives are continuous. And finally, we say that a transformation is one-to-one if it does not send two distinct points to the same point, which really means that a one-to-one is kind of the same definition that we had from back in Calc 1. Or no, that's not even Calc 1, that's algebra. So a one-to-one function is something that has an inverse. So transformation is one-to-one if we can also undo the transformation to freely change back and forth between the two regions that we're looking at. And finally, we'll take a look at a theorem that says if we have a transformation with both G and H continuous, so both of our functions, which when we see G and H, think that these should be our X and Y functions. As long as they're continuous, then our transformation will map one boundary onto the other boundary, which is going to be particularly helpful if we're trying to figure out what the image of our transformation will look like. The image simply being, if we have one region, its image is what it looks like after it's been transformed. So if we're trying to look at the new region, the best way to do that is to look at the boundaries. So we're just going to transform the boundary of one region to find the boundary of a new region. So let's put that into practice using the example below. So we'll have a transformation defined by the equations x is equal to u squared minus v squared, and y is equal to 2 times u times v. So find the image of the square given below. So it's the square that exists between 0 and 1 for both u and v. So, like we said a moment ago, if we want to know what this image looks like, again, image just being what this transformed region turns into, we should look at the boundaries of this region. So we'll start with S1, which is the bottom of the square. And along that line, V is 0. Notice V is along the vertical axis, U is along the horizontal axis. So V is equal to 0, and U is in between 0 and 1. So we'll plug in what we can. X is equal to u squared minus v squared. Since v is 0, it means x is just u squared. And y, which is 2 times u times v, is going to be 0, since v is always 0. So the x-coordinate can be anything between 0 and 1, and the y-coordinate is always 0. So if we're looking at the image of S1, it's going to be the line segment along y equals 0 between 0 and 1 for x. All right, then let's take a look at S2, which is that vertical line. Along S2, we know that u is equal to 1, but v is a free variable. It'll be between 0 and 1. So we'll take a look at our equations. X, which is u squared minus v squared, should become 1 minus v squared. And y, 2 times u times v, should just be 2v. Meaning that v is y over 2, giving us the equation x equals 1 minus y squared over 4. So some kind of a parabola there. And it'll be a parabola that opens up to the left, since it's x equals a negative y squared. Let's take a look at S3 being the third side of the square. It's along the top of the square. And along the top, v is equal to 1, while u is a free variable that gets to float between 0 and 1. Do the same thing, find equations for x and y. This time, x should be u squared minus 1, while y is equal to 2 times u times v, which is 1. And I can substitute that in. U is going to be y over 2, giving us the equation x equals y squared over 4 minus 1. So that's another parabola, but this time we have one that will open to the right, since x is equal to a positive y squared. And lastly, we'll take a look at S4, the left edge of this square. Here we have u equal to 0, while v is free to float between 0 and 1. Which means that x is equal to negative v squared, since it'll be 0 minus v squared, while y is equal to 2 times 0, so 0. Which means that this will be the line segment along the line y equals 0, where x can float between 0 and negative 1. And so v is between 0 and 1, x is in between negative 1 and 0. So if we take a look at a picture of that image, here is what we get. So S4, which was in purple, is going to get mapped to that section labeled there. S1 was the other segment along the line y equals 0. It'll be the right side of this shape. Then we know that S2 was the parabola that opens to the left. So it should be this red line hanging out right here. While finally, S3 was the other parabola, but it's the one that opens to the right. So it is this edge right here. And for the sake of clarity, I'm going to change our blue line to be a different color so it shows up a little better against this diagram. Let's use orange. So that's a color we haven't used yet. Come back up here, do the same thing. Change that to orange, and also that little segment over there. Ooh. But then orange blends into the other square. Oh well. Come through and label each of these S1, S2, S3, and S4. All right, next we'll define the Jacobian, being the partial derivative of x and y with respect to a partial with both u and v. So how are we going to set all of that up if x and y are both functions of u and v? And this will be defined as the determinant of the matrix provided, where we'll take partials of x across the horizontal direction, across the top of the horizontal direction, partials of y are across the y direction, or the bottom direction, the bottom horizontal direction. There we go. partials of u go down the first column and partials of v go down the second column. So again, if we kind of restate what this thing is, this is the partial derivative of x and y with respect to u and v. And it's, again, the determinant of that matrix. So if we multiply that out, it'll end up looking like the partial of x with respect to u times the partial of y with respect to v minus the partial of y with respect to u times the partial of x with respect to v. So we'll take the partials of each x and y with respect to both u and v, and then take the difference between them. I don't want to dwell on this too much because we're going to see a nicer example when we look at polar coordinates of how this Jacobian can really come into play. But for now, we'll just work with this definition when we need to. So if we define a change of variables, so transformation is a C1 transformation, which, remember, means that all of its first order partial derivatives are continuous. So we have that C1 transformation whose Jacobian is non-zero and maps a region that's S, which exists in the UV plane. So we have our region S is taking the U and V plane and putting it together into the region R, which is where our variables X and Y exist. Further, assume that F is continuous on R and that we have nice regions for R and S. And as long as T is 1 to 1, except possibly along the boundary of S, then we get that the double integral that we're used to taking in our regular region R, which is where we have our variables X and Y, we can change that into a double integral over the region S, where we've changed all of our variables to U and V, which is, again, why I said at the beginning, think of this like it's a complex U substitution. Also note that we have an absolute value on that Jacobian. So it won't actually matter which order we take those derivatives in. We'll just take each of the partials of x and y with respect to u and v, multiply enough together so that we have each variable show up once uniquely, and then take the difference from the other two partial derivatives. So enough of that. Let's try and put it into practice. So we're going to evaluate the double integral over our region R of the function y dA using the change of variables that we established in the first example. R is the region bounded by the x-axis and contained within the two parabolas y squared equals 4 minus 4x and y squared equals 4 plus 4x, which, again, we should see was the exact region we transformed earlier. So if we want to set this all up, we can start by using the formula that we just established, or the theorem that we just used, which said that the double integral over R of y dA is equal to the double integral now on our region S, where y is equal to 2uv, and we'll need that Jacobian, in fact, the absolute value of that Jacobian, which is the determinant of x partial u, x partial v, y partial u, y partial v, and this is du dv. Let's try that again. Du dv. Okay, so if we try and plug in what all that's going to look like, well, our region S is just that square that we had set up from earlier. And along that square, we had both u and v going from 0 to 1, which means that we don't have to integrate over functions in our bounds. We can just have standard definite integrals where we have a nice rectangular region, in this case a square region, and all our bounds are just numerical values, scalar values, I suppose we should say, which makes things pretty nice. So keep going with the rest of what we've got. 2uv is what we had there. Now we'll have the absolute value of the determinant of that Jacobian. So the partial of x with respect to u should come out to 2u times the partial of y with respect to v, which also comes out to 2u, minus the partial of x with respect to v is going to be negative 2v, times the partial of y with respect to u, which will come out to 2v. And du dv. Clean this up a little bit. We still have integrals going from 0 to 1 based on that region S that we looked at earlier. We'll have 2uv times the inside of that absolute value is going to be 4u squared plus 4v squared du dv. And unfortunately, we don't have to think too hard about that absolute value since both of our terms on the inside came out to be square terms. So that value is already going to be positive. So the absolute value won't end up changing anything. So we did not need, so applying the absolute value just means that we still have 4u squared plus 4v squared. All right, and we can do that integration relatively easy. When I did it, I got 2. So feel free to check that on your own. If we make one last remark, which would be just to look at what would happen if we tried to do this thing originally as an iterated integral. We could still plug in value or functions for x and for y. X we know went from 1 minus y squared over 4 to 1. Actually, that's backwards, isn't it? Let's try that one more time. The left side of that region would have been y squared over 4 minus 1. And the right side of that region would have been 1 minus y squared over 4. Again, just transformations we found from the first example. Y was going to go from 0 to 2, and we'll be integrating the function y, first with dx, then with dy. So that was our double integral before we made the u substitution. And we can see that in some ways at least, making this change of variable meant that our integration was considerably simpler. We did not have to deal with extra functions being plugged in after we take an integration. So that's the power of change a variable.